So good afternoon, everybody, to this 11th lecture in CFD. As I was just saying, today we will continue with nonlinear conservation laws, and today we will start to look at numerical schemes on how to solve them. But as usual, I would like to do a very short summary of the material from last week, and that's essentially summarized here on this screen that you should be able to see. So we looked at the Burger's equation, which is written here. It's the Burger's equation is a nonlinear conservation law, which can be written in the form ut plus f of u derived with respect to x being 0 in 1D. And this f corresponds to a flux function because it really acts as a flux, in an integral view. Whatever comes into a cell from the right, from the left, and whatever leaves the cell from the right. That's what the flux really means. And what we have done is we tried to see what the exact solution of the Burger's equation looks like, using some arguments also from the thermodynamics. And what this is called is a so-called Riemann problem. A Riemann problem is a problem where you just look at the solution if you have a step in your initial data. And typically one can then separate two different cases. One case where UL is larger than UR. UL is the solution on the right, and UR is the solution on the right, on the left and the right. So that's in the first case when UL is larger, and in the second case when UL is lower than UR. Now what happens in the first case is that the speed of the characteristics corresponding to the left side is larger than on the right side. So that means that the left side is essentially overtaking the right side. And this overtaking means that this discontinuity that we have here is essentially surviving as a shock in the future time evolution. And this shock moves with a speed s, which is the shock speed. And this shock speed can be calculated via the Rankine-Hugoniot condition, and in the case of Burger's, only in the case of Burger's, this will reduce to 1/2 of UL plus UR. And in this case, if I just try to plot that with in a space-time diagram, I may have the shock, developing here, and then I have characteristics from the left going into the shock, and characteristics, a little bit of inclination, and characteristics from the right also going into the shock, being absorbed in the shock. So this would be the situation for the first case. The second case is exactly the same as the first one, just switching the position of UL and UR, so meaning that UL is now lower than UR. That means, again, if I'm trying to plot that in a space-time diagram, it means that the characteristics from the left have a lower speed than the ones from the right. So it would be something like that. And then we were thinking about, at the end of last hour, what happens in this triangle between those characteristics. And it turns out that what we will see there is an expansion fan. So that means the exact solution would then be something like this, where this point moves with the speed of UL, and this point moves with the speed of UR. And in this space-time diagram, kind of look like characteristics that kind of fan out between UL and UR. So these are the two basic solutions, and all the solutions of Burger's can now be constructed as a superposition, or combining these two basic solutions together. Again, just to kind of summarize. So in the first case, we have a shock which moves to the right, and here we have an expansion fan that forms between UL and UR. And this is not just for burgers, this really appears for all types of nonlinear conservation laws. And homework number 4, when you're going to look at the shock tube, which is a standard flow case for the 1D compressible equations, you will see exactly the same types of flow features appearing. And all the methods or the characteristics that we looked at now, namely the shock speed and the expansion fans, you can then also see in those solutions, and you can even measure. You can even measure the shock speed and compare to the theoretical result. So now I guess the only question that remains is that what we have looked at here is for a truly hyperbolic problem without dissipation. Now, maybe a question would be, what is the connection of these results to a real life problem, so a physical problem? And actually, it turns out that these type of features, so the expansion fans and the shocks, that they also appear in really physical problems. I was just saying the shock tube will show exactly that. But of course, we need to realize that the hyperbolic problem that we considered, the hyperbolic problem is typically an approximation to the physical problem that we actually want to consider. So it's an approximation to the physical problem, and the physical problem usually has some dissipation or some viscosity or dissipation present. So that means if we look at the Burgers equation, which looks like this: ut plus u squared divided by 2 derived with respect to x being 0, that is actually an approximation to the physical problem, which could look like this, where we have on the right hand side some viscosity times uxx. As we will see later, a viscosity or a viscous term will always be written as a small number, the viscosity times the second derivative in space. So this nu is a small viscosity. And can be, to just get kind of the bigger picture, and can be neglected. But in the physical world, of course, it would be present, but it would mean that the physical shock that one gets, a physical shock, is therefore a solution to the problem on the right, where there's a little bit of viscosity present, and this viscosity then acts as smoothening out the really discontinuous solution to the hyperbolic problem. So that means that the physical shock is therefore not exactly discontinuous, but still a very steep step. So that means if we kind of have the solution to the hyperbolic problem, which would be maybe a shock like this. This is kind of u, and this is x. This would then be in the physical problem something like this. So I try to plot it. So it's a very steep, but still continuous step function here. And this width of this step, so the region over which the solution u changes in a continuous way, this is a very small width, and I guess one can write that this is on the order of this viscosity. Of course, I mean the units are not exactly correct, but if you normalize that in the correct way, then this will be on the order of this small parameter of the viscosity. So that means the smaller the viscosity, the steeper this step is going to be. And in real life problems, acoustic problems, I mean, these type of shocks, they have a few nanometers, micrometers size over which the density, for instance, changes. Okay, so the shocks are actually problems that appear in reality as well. So it's not just a mathematical construct that we have now invented here for hyperbolic problems. Of course, that also makes it then important to understand that the second law of thermodynamics, which we used, the entropy condition, that I have not mentioned here, but the entropy condition that actually made this shock to be present and here an expansion fan to appear, that this is really motivated from the underlying physical problem where certain feature or certain effects happen, maybe the shock when you have characteristics running into each other, but other effects do not happen, namely having expansion shock where characteristics would emanate out of a shock, as the opposite example for the expansion. Okay, so with this, I would actually like to close kind of the summary from yesterday, from last week, and the summary about the exact solution of the Burger's equation. What we will, what we are working on right now is to also provide on the homepage another example of a more complex Burger's equation problem, which you can maybe try to do an analytical solution as well, but then also use a numerical method to calculate it. But this is still in progress and will be updated on Canvas quite soon. So do you have any questions about the kind of the first part, the analytical solutions that you would expect from a nonlinear conservation law? Because if not, then we would actually continue to the next part. And I guess if I counted well, this would now be letter C, and that is numerical methods for hyperbolic problems. So now that we know how a solution looks like and what we would expect, and we talked about the conservation properties, the flux formulations, and so on. Now we need to design numerical methods. And I would like to start with the first example. Example number 1. We want to solve the Burger's equation. So we write it like this. So ut plus u times ux is 0. As if you remember, this would then be called the non-conservative formulation, or the convective formulation of the Burger's equation, where I take out the speed, or the quasi-linear formulation, where I take out the speed u times ux. Of course, in order to be able to solve that, I need to give some conditions at initial time, and I would say that we have just two different solutions, 1 and 0. 1 would be for x being lower than 0, and 0 for x being larger equals 0. And of course, from what we have just discussed, we know what the exact solution is. The exact solution is a shock. So this continuity moving to the right, and it does that with a speed s being, well, it's the average between ul and ur. So that means in this case it would be 1/2. So with a speed of s being 1/2. This comes from the Rankine-Hugoniot condition. So we know exactly what should come out from the analytical solution. And now let's just see what happens if we do a straightforward discretization of this. Okay, so how do you want to discretize that? Well, if you look at the equation, we have a time derivative and we have a space derivative. And we have done that before when talking about the advection equation. So I guess a forward time, backward space scheme would be good. So forward time, backward space, or as we also can call it, it's a simple upwind scheme. Well, how does this look like? Well, Ujn plus 1 is Ujn minus delta t divided by delta x. And now comes the speed. In this case, the speed would just be Ujn times Ujn minus Uj minus 1n. So this here is an upwind scheme. It's forward time, backward space. Backward space comes from this bit here. It's backward in space, so it's it takes j minus 1 and j, and it's a forward time because here everything is at time n, and the only new time is here on the left. Of course, now we also need to discretize our initial condition, so I can write Uj0 is, well, it's either 0 or 1. It is 1 for j being lower than 0. Now I'm kind of going into the space of the indices, and if j is larger than 0, it would be 1. That would kind of indicate that that my mesh would look like this. If this is x, and here would be x being 0, then I have my grid points located kind of like this. Of course, also in time, something like this. Right. This distance obviously is delta x. This distance is delta t. And I would call this to be index j being 0. This is j1 and so on. And this would be j being minus 1. And in this case, that explains why I would discretize my initial condition in this way. Okay. Now let's play computer and do a time integration of that. So we compute. Fortunately, it's very simple. So I just calculate what is Uj1, which of course is Uj0 minus delta t divided by delta x. Now we have Uj0 here, and then we do the difference between Uj0 minus Uj minus 1, 0. So what we see now is that what this rule means is that I update, the grid point value at Uj from 0 to 1, so kind of going one step in time, is dependent on this difference here. And this difference, Uj0 minus Uj minus 1, 0, this one is actually 0 for all points except at the case where j is being 0, because only then I have, U0, 0 is 1, and is 0, I'm sorry, and Uj minus 1 is 1. So only there I have a difference. But, and now comes the problem here, at Uj0, then actually it turns out that the speed, so the multiplication factor, is also 0. So this one, so this difference is always 0, except in j being 0. But for j being 0, we have Uj0 equals 0. Okay. What does that mean? Well, that means that this term here is 0 for all j's. And what we get as a result is uj1 being uj0. And this is valid for all j. And of course, this continues for the next steps as well. So we get uj2, uj3, and so on. They will all be the same. So that means our solution to the numerical scheme is, well, it's not moving. The solution of the numerical scheme converges to, well, what does it converge to? It converges to u of x comma t being the same as u0 of x. Obviously, this is incorrect. And I'm really using here the word converge because I can now refine my mesh in delta t and delta x. So I can make my grid spacing that I have chosen here, so delta x and delta t, I can refine that and get smaller and smaller and smaller, where in principle I would expect that I get better, but actually it turns out it is not getting better. And this is actually a fundamental problem for conservation laws, nonlinear conservation laws. And now maybe the question would be, why did I end up with this? What was the problem that I did here, such that I got a result which was actually quite incorrect? I kind of stopped my discontinuity from moving. Well, the problem, unfortunately, I already did at the very beginning. My problem was at the stage when I wrote down my governing equation. And this is something that you should really keep in mind for nonlinear conservation laws. You should not write down the equations in this non-conservative form or in this quasi-linear form, because then you may end up with situations like this, when the fluxes are in fact incorrectly treated, because the flux, so the f, keep in mind there is the original formulation of the Burger's equation would have been ut plus f of ux being 0, with this f being, well, u squared divided by 2. The flux would have been u squared divided by 2. So that means on the left side, where the solution is 1, there my flux, actually maybe I should not write it here, I should rather write it when I wrote the initial condition here. Let me move this a little bit up. So here, let's do that. So my flux for the situation when x is lower than 0, so I can write f of u0. This flux actually would be, well, if you go in, it's 1 squared divided by 2. So this would be 1/2. And the fluxes here on the other side would be u0 being is 0. So the f, the flux function evaluated. And of course, there's a discontinuity between f at 0, so it goes from 1/2 to 0, and of course that gives you then a df dx, which then should be accounted for in the transport behavior of my shock. But still, the fact is that I have a transfer of f on the left side, and I have no transfer on the right side. So that means that in principle, I should have my thing moving to the right. But that is not what is happening. And meaning that actually the conservation of my solution is not fulfilled in this particular form. So the conclusion of this is in order to get correct results, we actually would need to look at a better discretization. So instead of approximating the quasi-linear form, we should try to approximate the conservative form. And I just wrote it up on the top. So that's ut plus f of ux being 0 instead. And then you would not have this problem. So that means from now on, we will actually look at the conservative form and discretize that. We will get back to this point a few more times later on. Okay, so this was my motivating example for how to formulate numerical schemes for conservation laws. Let's now go back into stability and what stability kind of means in with a more physical meaning when it comes to conservation laws or convection-dominated hyperbolic problems. And I write here that this is actually a continuation because the formal results that I will show you here, we have already obtained, but I would like to show you now a more intuitive way of perhaps assessing the stability for a convectively dominated problem. And this is now chapter 1.1, and it's called the CFL condition. Now, it's important to realize that that the CFL condition comes, I mentioned it before, that's from 1928 by Courant. Write it better, Courant, Friedrichs, and Levy. So these three researchers, and they did it in 1928. So that means actually the CFL condition for stability was done before people understood the von Neumann analysis or the von Neumann stability theory for partial differential equations. So that means that the kind of the more physically dominant solution was discovered earlier. So what does the CFL condition actually mean? Let's look at the advection equation. The reason why we look at the advection equation, not the Burger's equation that we just did before, is the advection equation is linear, so all my characteristics are kind of straight lines. In the nonlinear case, it's a little bit more complicated, but the same principle works as well via linearization, which we'll talk about in a second as well. But let's start with the advection equation. So we have du dt plus a times du dx, du dx being 0. And as you remember, the von Neumann analysis which was a necessary and sufficient condition, the von Neumann analysis gave us that sigma, which was defined as a times delta t divided by delta x, should be lower equal 1 if I'm using the forward time backward space scheme. So that means we know from the von Neumann analysis that there is actually a stability limit. But now to understand the CFL condition, it's actually quite instructive to just plot this condition in a space-time diagram. So I'm plotting it here. I have delta x, I have x here, and I have t. Now let's say that I have my grid point xj minus 1, and I have my grid point xj, and this here would be time tn, and maybe this would be time level tn plus 1. Of course, then I will have another grid point here, and I have a grid point here. Now I know for the forward time backward space scheme, my stencil would be something like this. because the forward time backward space scheme looks like this. Ujn plus 1 is Ujn minus a delta t divided by delta x, Uj minus Uj minus 1 at time n. So the points involved in my scheme are this one, and the solution would be this one. Okay. Now this is for the numerical scheme, and then for the exact solution, if you now just think back what it actually means to have an advection equation or a solution to an advection equation, we know that we have a characteristic that kind of perhaps looks like this. Of course, it should be only one line. It's not nicely drawn. Something like this. That would be the characteristics, and that would correspond to dx over dt being a. Okay, so now the question is, how do I need to plot this graph for a stable case, and how would it look like for an unstable case? And it turns out that what I drew here, this one would correspond to a stable situation. Stable because, and now we can actually go in and check, because it would actually turn out that a times delta t divided by delta x would be lower equal 1 for this situation. Why is this the case? Well, if I say that this is delta t, and this here is delta x, then I see that this blue line, so the characteristics, would actually have a slope which is larger than what I would get from delta t divided by delta x. And delta t divided by delta x here, so this part would essentially correspond to the slope of the left side of this triangle that I have written here in green. See what I mean? So the slope of this characteristics A is such that the blue line would lie between the slope of the left side of the triangle and the vertical line of the triangle. This one would correspond to 0, and this one would correspond to a slope which is given by delta t divided by delta x. Okay, so how would now a unstable case look like? Well, I just move this over here. So, how would now an unstable case look like in a space-time diagram? Well, it needs to be a case where the slope of the characteristics is actually such that it is lower than delta t divided by delta x. So it would actually be something like this, because then it would, so the slope a, so again dx over dt, which is a, would then be outside of the triangle formed by delta t divided by delta x. This would correspond to an unstable situation in the sense of von Neumann analysis. Also unstable, of course, would be if it would look like this. That would also be an unstable situation. So that means from just drawing the von Neumann stability analysis, the result from the von Neumann stability analysis, we realize that it's the region inside this triangle here, which would give rise to a stable integration. And as soon as you're outside of this triangle, you would be unstable. Okay? And of course, now the question is, how can we kind of give a physical interpretation to this problem? Well, that's exactly what the von Neumann analysis says. Because we can now go back to a concept that we have discussed earlier in the course about the domain of dependence of numericals, or the domain of dependence of a partial differential equation. And it turns out that the characteristics, in this particular case, it's just a line, the characteristics defines the domain of dependence for the exact solution. The domain of dependence is, you just follow the characteristic backwards. And then you know, okay, from the previous time, you essentially need to take this value and transport it to the future. So that's the domain of dependence for the PDE. Domain of dependence for the partial differential equation. But now the question is, what is the domain of dependence formulated for the discrete problem? And actually, it turns out that the domain of dependence for the discrete problem is exactly this yellow region. So this we can say is the domain of dependence of the forward time backward space scheme, the one that I just formulated here, because it depends on the values here and here to calculate this value, which then gives you the shape of this triangle. Now, this consideration gives you the basic idea of the CFL condition. It means that a necessary condition for stability for this hyperbolic problem for stability is that the domain of dependence of the finite difference scheme includes the domain of dependence of the partial differential equation. And of course, this makes also sense if you think of it, because it means that the domain of dependence of the partial differential equation is this line here. So the information needed to calculate the value at this point is along this black line. So that's the characteristic that follows, that goes into that point here. So that means in order to know what the solution at Tn plus 1 is, I just need to follow the black line backwards. And now, in order to give the numerical scheme even a chance to predict this value correctly, it needs to be such that the grid points that are needed or that are used to calculate the new point need to contain that original point that I would need to have. In the two unstable situations that I drew here, if we just take this one, then we know that the solution principle comes from here, but I would like to solve it with just these 2 points. And obviously, this cannot work because these 2 points do not know what the solution is doing there to the left. Or the same thing if I take this line here and I go here, these 2 points do not know what the solution is doing there on the right. So that means it intuitively kind of makes sense that I require that the domain of dependence of the finite difference scheme, so my stencil, is actually bigger than the domain of dependence of the PD, so the region where the solution comes from to the point I want to calculate the solution. I guess now this explanation also explains again the definition of domain of dependence, as there was a question in the chat that I should explain that again. So I guess that's also clear now. Okay, so yeah, so that means that an intuitive definition for stability is that the domain of dependence of the finite difference scheme is bigger. And as I said, this makes sense. Everything else would kind of not be possible. Now, it turns out that this is a necessary condition. It's not sufficient So it's not that you can be sure as soon as you have a big enough stencil that everything is going to be stable. Also, that makes sense because just knowing the right information does not mean that you do the right thing with it. So therefore, it's only a necessary condition. And as I was now saying, this criterion or this condition is called the CFL condition. And this comes from a nice paper in 1928 when they were talking about convectively dominated flows, so hyperbolic problems which had characteristics that transported information in certain directions. Now, this is a quite formal definition that I wrote here. The necessary condition is the domain of dependence and so on. There's actually kind of a more sloppy kind of way of interpreting this, in particular for the forward time backward space scheme. But in fact, it actually works for most other time integration schemes as well. One way of viewing that is that if this is the information that travels, the idea is that this information is not supposed to travel more than one grid point. That's what you kind of see here. It should not travel from xj minus 1 to xj plus 1. It should just travel within one grid point. Of course, that's true for the one-sided stencils. But it's kind of it's a good idea which directly then relates to a convection speed, which is the slope of the characteristics and kind of the flow of information. So the information or the solution should not travel more than one grid point. That's kind of the sloppy way of describing the CFL condition. Now, so that's the CFL condition, and then the sigma. I mentioned it also before, but it's maybe good to mention to repeat it. So the sigma here, so this A times delta t divided by delta x. A times delta t divided by delta x. This is typically called the Courant number, and it relates the convection speed A to the, let's say, the geometry of the mesh delta t divided by delta x. Now this is in 1D, but you can find similar things in 2D when you can define Courant numbers in different directions. Yeah. Now, I was saying that this is only a necessary condition. It's not a sufficient condition. And also that we may want to just discuss on a quick example. Consider the central finite difference scheme. So same problem, convection or advection equation, but we look at a central finite difference scheme, so finite forward time central space. But now we look at it from a point of view of the CFL condition. So if I just try to plot that, we have xj, we have xj plus 1, we have xj minus 1. So this here would be time tn, and here maybe tn plus 1. Well, find the forward time central space scheme would be something like that. So uj n plus 1 is ujn minus a times delta t divided by delta x squared, not squared, by 2 delta x. So, and then here I do the differences between uj plus 1 minus uj minus 1 at time n. So that means if I'm plotting that in this space-time diagram, it would look like this, that the solution here at the tn plus 1 would depend on a triangle like this. So my domain of dependence would be something like this. Another question is, what does the CFL condition give with this domain of dependence? But this we will look at in 15 minutes after the break. So I will stop now the recording, and we will continue at 1:15. Yeah, so welcome back to the second hour. So we were just looking at the CFL condition and what happens with the CFL condition for a central scheme, the forward time central space scheme. And now it would turn out that this scheme should in principle be stable for all the characteristics that kind of look like this, or look like this, anything into this in this yellow region. Stable stable with the CFL condition. But now, of course, the question is this really the case? Because we need to kind of be able to independently check whether our stability result is correct. So we do a von Neumann analysis, but now we do it for the central scheme. And of course, you remember how this works. We look at one Fourier mode. U hat k n times e to the I k x j. So that's our ansatz. And we put that into the fully discretized equation. And then we get our complex amplification factor. So what you get in the end, you can do that at home. What you get as a result is u hat k n plus 1 is u hat k n times 1 minus a to the delta t divided by 2 delta x times e to the I k delta x minus e to the minus I k delta x. I guess this is not further surprising. So we will have, I mean, this is the same prefactor, and here we get just the central difference. Now, this stuff here we can summarize with minus I times sigma sine of k delta x. And of course, this sigma is the same as we had before, a times delta t divided by delta x. But now, with all these abbreviations and calculations, we now see that our g hat of k will be 1 minus I sigma sine of k delta x. So that is our complex amplification factor. Now, what we're interested in for determining stability, it's the modulus of this g hat. So g hat of k, absolute value. Well, this is a complex number now, and the absolute value of a complex number is the squares, or the absolute value squared is the sum of the real part squared plus the imaginary part squared. So in this case, this will be 1 squared plus the imaginary part squared, which is sigma squared sine squared delta x. And now, what you see from this is that 1 plus a square is obviously always larger than 1. So this is clearly larger than 1. And what happens if you have something that is larger than 1, which is not a function of delta t? Well, it means that this is an unconditionally unstable scheme, as simple as that. So that means there is no combination of delta t and delta x that would make the time integration of the advection equation using the forward time central space scheme stable. So this is unconditionally unstable. And I guess this shows us a very important result that we always need to keep in mind, that although the CFL condition is fulfilled, and with CFL condition being fulfilled, I mean that we can choose some blue lines that line within the yellow region. So characteristics that lie within the domain of dependence of the central space scheme. So although this condition is fulfilled, the scheme is unstable as per the von Neumann analysis. And of course, this is absolutely possible because the CFL condition is only a necessary condition, not a sufficient condition, as opposed to the von Neumann analysis. So that means the CFL condition is useful. It gives us a physical interpretation, but it's also, you need to take it with some care because it is only a necessary condition. But what we have now learned from this is that if you want to integrate the advection equation in a stable way with an upwind scheme, you need to make sure that the upwind scheme, or the domain of dependence of the upwind scheme, always looks like I indicated in this plot here. It needs to be such that the discretization has the same kind of direction as the characteristic has, so that you can always fulfill the requirement that the domain of dependence of the difference equation is larger, or is containing the domain of dependence of the advection equation in this case. So in this case, just the characteristic. So maybe I can just say that as one conclusion here. Upwinding always in the direction of the characteristics, or the speed, or characteristic speed or velocity. So that's an important conclusion now from all of this. Okay. So now we have introduced the CFL condition. We have a kind of an idea of why the upwinding, or this last conclusion here, needs to be done in this way because of the domain of dependence and so on. Let's now try to implement that in a numerical scheme. So how can we, create a numerical scheme that actually, fulfills this idea of upwinding? And for this, I would like to look at another example. That's example number 2. And again, we take the Burger's equation. And the Burger's equation is kind of a simple example of an equation which is nonlinear. Just write it down once more. ut plus f of u x being 0, with, of course, this f of u being u squared half, or f prime of u, which is the speed, which is u. Now this time I'm taking, again, an initial condition. I do it slightly differently. I say it's -1 and 1 for x being lower or equal 0, and for x being larger than 0. So that is now the opposite situation that we looked at before. Namely, we're in the situation that UL is lower than UR. And that means that we're actually not having a shock, but we actually have an expansion fan. So if I draw that, if we have t and x, and here we have our grid points. We have one here, we have one here, we have one here, and so on. These are my grid points. Then the solution or the characteristics would look like this. They go to the left on the left, and they go to the right on the right. Simple as that. Then here in the middle, it depends a little bit of whether there's a larger equal or not. But that's not so important for the time being. So now, how should we now do an integrate, or how should we implement that in an upwind scheme? Well, it means that if we want to do a stable integration on the right side, so on this side, if I want to do an upwinding here, so an upwind scheme, use, well, xj and xj minus 1. So that means on this side, my discretization would be something like that. Uj n plus 1 is uj n minus a delta t divided by delta x times uj n minus uj minus 1 n. Actually, this should be not an a here of, well, I can use an a here if I want to do it like that. I consider this to be the step. So something like that. So the important thing is that I will have here these 2 points being used. In order for being stable on the other side, so on the left side, then the upwinding would actually be, I would need to go in the other direction. So my upwinding here would be uj and uj plus 1 that I would be needing. And of course, I could write down now the discretization as well on the left side. So that means what we see now directly for this problem, we need to use different discretizations depending on the local speed. In this case, the speed is the solution. So I can say the local speed, the local solution. On the left side, so here, I would need to have an upwinding with uj or xj and xj plus 1. So that I actually go to the left. And on the right side, I will need to have an upwinding that goes to the right. Otherwise, I would not be stable. I would just blow up. So that means depending on how my solution is, I need to have a different solution, a different discretization. And of course, that's a little bit, I guess you understand why it's needed, but it may be a little bit cumbersome to implement. And therefore, I would just like to show you kind of a more general way on how this can be done, or how this is being done in numerical schemes, to sense on its own in what direction you would actually need to integrate. The basic idea here is that I would write that I would write a general update scheme. I can maybe start like that. So I would like to write like this. So I say uj n plus 1 is uj n minus delta t divided by delta x. And then in this brackets, I write hj plus 1/2 n minus hj minus 1/2 of n. Something like this. And what I just wrote here, this now is something that we would call the conservative formulation, or a conservative scheme. As conservative finite difference scheme for a nonlinear conservation law. Because now you see there's actually no bias in either direction. I just say that here it's h of j plus 1/2 and h minus 1/2. Of course, now the question is, what is this h that I have introduced here? So why do I need to introduce something else? Well, the basic idea now is that locally around the grid point, so if this is x, this is maybe index j, this would be j plus 1, and this would be j minus 1. So around this grid point, we would kind of define a little box. Now I lost the black line. So now the black line is back. So I would consider two boundaries, one located between j and j plus 1, which I can call j plus 1/2, and one located between j and j minus 1, which I can call j minus 1/2. Now these guys, h at j plus 1/2 and h at j minus 1/2, these guys now can be considered as being the fluxes over these two boundaries, the two green boundaries. Now, obviously, if I formulate it in this way, this arrow here would be the flux at j plus 1/2, and this one would be the flux at j minus 1/2. So this h here, these are approximations to the fluxes that come in or go out of this kind of little green box that I have now done or constructed around j. And because now this scheme is really based on fluxes coming in and fluxes going out, I will call this conservative, because as soon as my calculation of the flux is correct, so just thinking back of an integral form as before, it's just I add whatever comes in and I subtract whatever goes out, and that is the change to my value. I would always automatically fulfill the conservation properties, because everything is just based on the fluxes. Okay, so I guess it's kind of obvious that this is a good way of discretizing the conservation properties of my scheme. Now, of course, the next question is, okay, that's of course very good, but how do I now make sure that I get the upwinding in the correct way? And for that, there is a kind of an easy way and a slightly more complicated way. I will start with the easy way, where I just tell you how we can calculate this h. And then in the second part, I will show you kind of a more formal way of how we can design a scheme that does it automatically. So the easy way of how now to exploit this new formulation with the h's is simply that I say h at j plus 1/2, that this can just take two different solutions. Either it's f of u j plus 1, or it's f at uj, and I take it to be j plus 1 if f prime of uj is lower than 0, or it's the opposite if fj of uj is larger than 0. And I do the same thing for the other flux term at j minus 1/2. I also say that this is f of uj or f of uj minus 1, and this is if f prime of uj is lower than 0, and this is if f prime of uj is larger or equal 0. But what does this do here? Why did I write it like that? Well, it just turns out that this f prime, of course, that is the speed, right? That's the first derivative of the flux function that gives you the speed. So this f prime here, so this condition here just is essentially evaluates, is my characteristic going to the left or is it going to the right? Or rather like this, to the left or to the right. And then depending on whether it goes to the left or to the right, it just says that, well, if it goes to the right, it just makes sure that it takes differences like that. And if it goes to the left, it makes sure that it takes differences like this. So this is kind of the easy way of using the conservative formulation to make sure that I'm always doing the upwinding in the correct direction. Now, while this is kind of the easy way, there is also a slightly more complicated way, which I don't want to spend too much time, because that we'll discuss later on also with Ardeshir in the finite volume case. But I would just like to add it also here because it fits into the topic. So more general. A more general way of doing that. Actually, the idea is that I will define two different fluxes. I will define a flux that goes always to the right, and a flux that always goes to the left. So if I now say that locally, I define a velocity, Aj, which may be kind of f prime at uj. And in this case, for the Burgers case, this would just be uj for Burgers. Then I can define a flux, A plus, at this grid point, which is the flux that goes to the right. And this I can define as the maximum of Aj and 0. So this one only has a value if Aj is positive. Formally, the max I can write like this. This is 1/2 of Aj plus the absolute value of Aj. So this one is either Aj or 0. At the same time, I can also define a flux that goes to the negative direction, which will be the minimum of Aj and 0. And of course, that could also be written with an absolute value, which is Aj minus Aj. So this minus flux is either 0 or it's a negative number. So now I have actually done a split into a positive flux, which has a speed of A plus, and a negative flux, which has a speed of A minus. With this now, I can actually define the two different fluxes. I can define a flux F plus at J, which is just, Aj plus times Uj. And I can define a negative flux, which is F minus J, being Aj minus times Uj. So I have now again, I have a flux that is positive, or a flux that goes into the positive direction if there is a positive flux, or is 0 if there is no flux in the positive direction. And I have a one that goes into the negative direction. And this technique here is called a flux splitting, because it splits my flux into something that goes positive, F plus, and something that goes negative, which is F minus. And now the cool thing is, now I can actually go there and say, okay, coming back to my H's, so the Hj Xj minus 1/2, well, that is the fluxes. I can go to my graph here. That would be the fluxes at this point. Well, that would be essentially it would be the positive fluxes that come from this point, and it would be the negative fluxes that come from this point. So it would be F plus from here and F minus from there. at this point, it would be the positive fluxes that comes from here and the negative flux that comes from the prime minus, and the negative flux that comes from here. So that means if I'm putting now indices here, this would be J plus 1, this would be J, this would be J, this would be J minus 1. Right? So now you see that the importance that for point J, I actually have a J minus and a J plus, but they go to different sides of the boundaries. So to different HJ minus 1/2 or HJ plus 1/2. Well, if I now put everything together, I can now write down that, well, HJ minus 1/2, that's the combination of the positive flux at J minus 1 and the negative flux at Fj. And in the same way that Hj plus 1/2 is the same as Fj plus and Fj plus 1, but then the minus. And now, if you put everything together, I mean, now we have written down all the equations here for the fluxes. If you put everything together, you will see that you will actually end up exactly in the way that we have already predicted from the beginning, that on the left side, on the right side, you will have a positive upwinding, and on the left side you have a negative upwinding. But of course, now written in a kind of a more general way, when we have really introduced this idea of a flux splitting. So we have a flux that goes to the positive and a flux to the negative. Arashia will later tell you how this can be generalized for also problems with multiple variables, like the Euler equations, where you first actually need to do an eigenvalue decomposition. You first need to get the characteristic directions. Okay, so this was now the idea of how to use upwinding. We actually still have one problem, which I have, well, in a more or less elegant way ignored here, namely the fact that, well, we have this guy in the middle, which we have chosen now the scheme to have characteristics that go away from the center. But of course, sometimes we have it like this, that they go together, and then we would have shocks. And now the thing is that the way that I just introduced here, that this would not work. This would not work for shocks exactly in the way that I described here. So for shocks, on the other hand, it is actually better to take central differences. But of course, then we have the stability problem, because central differences, as we just said, they are actually unstable. So therefore, there may be also options to use schemes over shocks, and one example would be the Lux-Friedrichs scheme. And I also would like to just write that down to kind of tell you that at times small modifications of numerical schemes actually give you a large change in the stability properties. So the Lux-Friedrich scheme, it's a central scheme, which essentially is just like this, n plus 1, and then now we write ujn minus delta t divided by 2 delta x times f of uj plus 1 n minus f of uj minus 1 n, like this. Now, of course, you would say, okay, now I just wrote down the central scheme again, but the trick now is that for the Lux-Friedrich scheme, I'll just replace this ujn with yet another central difference by uj plus 1 n minus or plus uj minus 1 uj minus 1 n. So the small difference is that instead of using just the value uj at n, I actually take the average of the two neighboring points. And this small change actually makes the scheme stable. The problem with this one here is that it's extremely diffusive. So you will not get a very good solution if you apply it everywhere. It's an extremely diffusive scheme. Okay, so with this, I would like to conclude this chapter about the CFL condition. So the idea of using kind of the direction of the characteristics to design a numerical scheme, and then also to use the idea of having different directions to construct a scheme that automatically detects in what direction it should integrate. So that was the idea of this conservative formulation, where we have approximations to the fluxes on either side of the grid point. Now, do you have any questions or comments regarding that part? Because if not, then I would actually like to directly continue to the next step or the next point, which is chapter 1.2, which I kind of already mentioned now. That is the method of the modified, not wave number, but the modified differential equation. I mentioned it in the way that I was saying that, well, this Lax-Friedrich scheme is a very diffusive scheme. Now we would actually like to understand how we can predict the properties of a numerical scheme just by looking at how it's how the fully discretized version is written down. I introduce it as a method to determine the stability again, but it actually does much more than just determining stability. But we can say that the idea is that it's an intuitive way to determine stability. So it gives us kind of a third way, or actually a fourth way of determining stability after we have talked about the absolute stability of an ODE, the von Neumann analysis, the CFL condition, and now the modified differential equation. The idea is that we actually look at the truncation error. So consider the truncation error that we have introduced earlier in the course. If you remember, this was the local truncation error. So it was located at Txj and Tn, and this was the difference between the exact PDE minus the discretized PDE, something like this. So P, which is the exact PDE, minus Pn, which is the discretized one. So the truncation error, if you think back, that was about the consistency. It tells you how well do we approximate the partial differential equation. That's the idea of the truncation error. So what is lost by going from continuous to the discrete system? We have done an example at the time. If you think back, we looked at the example of forward time, backward space. And for that, we found earlier that this T of xj and Tn was 1/2 A times delta x 1 minus sigma times uxx plus some stuff that was of higher order, delta x squared and delta t squared, something like that. So this is something that we have seen before. But now we would actually like to kind of see whether or not we can use this to directly tell you whether we have a stable scheme or not. Because if we now write our, so this is the truncation error. So this is what we have, this is the first error term that we get if we discretize the scheme. But what happens now if we retain this leading error term in the partial differential equation? Well, that would then mean that in this case, for forward time backward space, for the convection equation, it would actually mean that this was the equation that we wanted to solve. You know, this equals 0. This is what we wanted to solve. But if we now retain this first error term, we actually get the equation that we are solving, in fact, by using the numerical scheme. That means that we actually can just write here this term, a times delta x, 1 minus sigma times uxx, plus higher order stuff. But we see now that instead of solving the advection equation ut plus a times ux, or a hyperbolic problem, what we actually do is we approximate an advection diffusion problem. An advection diffusion problem, because this guy here, this is actually a diffusive term. And this prefactor, we can say that this is actually a viscosity. This is a new numerical. I write now numerical because this is a viscosity which is not a physical one, but it's a viscosity that comes in just from the discretization. So just to kind of make my sentence here complete. So if we retain the leading error term in the PDE, we see that this is the equation we solve instead of what we actually wanted to solve, instead of the original PDE, which was simply ut plus aux being 0. So instead of solving a hyperbolic problem, advection equation, well, we actually solve an advection diffusion problem. And this diffusion, so this additional term, that comes from the fact that we have discretized it using a forward time backward space scheme. So the additional term resembles a diffusion, so a viscous term. Viscous term with a numerical viscosity. So the viscosity parameter then is nu numerical, which is this 1/2 a times delta x, 1 minus sigma. So it's important to understand that the discretization leads to a leading error term that resembles this viscosity. So that means that instead of actually solving the advection equation, we solve, or we get a solution that is a solution to an advection diffusion problem instead, with this particular value of a numerical diffusion. Now, the question now is, okay, if I now accept that I'm actually obtaining a solution to an advection diffusion problem. When or under what circumstances is the solution of an advection diffusion problem stable? An advection is always stable. So there's no problem from the advection, analytically speaking. But a diffusion is only stable if I have a positive viscosity. If I have a negative viscosity, that would mean that I have stuff that is exponentially growing. Just think back of when we talked about the well-posedness, where we said that the inverse heat equation is not well posed because it would amplify exponentially small errors. So that means we only have stability if you have a positive diffusion coefficient. So that means stability now means, for the analytical advection diffusion equation, means that nu numerical should be larger than 0, or larger equal 0 perhaps. So, okay, if I just write that down once more, so we have the numerical viscosity 1/2 A delta x here, delta x times 1 minus sigma, and that should be larger or equal than 0. Of course, I can now simplify. A is positive, delta x is positive, so I get 1 minus sigma should be larger than 0. And of course, this just means that sigma is lower equal 1. And this is valid for A being larger than 0. And of course, this condition we have now seen 3-4 times before. It just gives me again this condition that that sigma needs to be lower equal 1 if I get a positive numerical viscosity afterwards, which I need for stability. There was a question here in the chat, which I think is exactly what I just said. Is it a general fact that always the discretization increases the viscosity, or can you say it can also be negative value for this numerical dissipation? Yes, it can be it can become a negative value if sigma would be larger than 1. Then my numerical viscosity would be negative, but then I know that it's unstable because the solution, the analytical solution to an advection diffusion equation with a negative viscosity will be unstable. So for a stable problem, I need to have a positive numerical viscosity. That is exactly the condition for stability. And now I get it, that this corresponds to the well-known CFL condition again, sigma lower equal 1. Now derived in yet another way. But now I said that, okay, I introduced this method of the modified differential equation as an intuitive way to determine stability. But actually, it's not just that. It also gives me kind of an idea of how my solution will look like. Because now I know that my solution is affected by a viscosity. And if you remember back when we talked about, if this was my initial condition, and then I was subtracting that to the advection equation, and we understood that maybe this here would be so if this is the initial condition, and this one would here be the exact solution at time, I don't know, t1 larger than t0. Then we have seen that depending on the value of the sigma, so the value of the Courant number, we get kind of different degrees of smoothing here, right? So this would then kind of be the numerical solution that I get. But now, with this derivation here at hand, namely that we know that instead of solving the original PDE, we actually solve an advection diffusion equation with a numerical diffusion that depends on sigma, we can actually understand that. We can also see that the larger, the lower sigma is, so that means the larger 1 minus sigma is, the more diffusion I have. And in the extreme case of sigma being exactly 1, then 1 minus 1 is 0. That's when I have no diffusion at all. So we can exactly understand why that my solution looks like this for, let's say, a high value of diffusion, and perhaps more like this for a lower value of sigma. So I can understand that this now means that I have larger numerical diffusion. And because it's a 1 minus, it would mean that sigma would go up like this. Then, of course, limited by the value of 1. And this is now something that we can directly see by just looking at the leading error term. So that essentially means if I have a first order scheme, when my leading error term is of second order, I'll get a diffusive term, which then gives me damping in exactly that way. And we can now see how much damping we get from discretization by just looking at the value of the numerical dissipation. Okay, with this, I would like to stop for today. And then tomorrow, we will continue with, well, trying to see whether there is other ways of, or whether there is ways around having this quite strong numerical diffusion. But this is then something that we look at next time. Okay, with this, I would like to thank you. And of course, if there's any questions, I'm here and I can answer that.